Well, welcome back, guys. We're back for some more torture, right?
Hello.
Okay, hope everyone's doing okay. Just a quick note about sig figs. It sounds like there's still a bit of a challenge. We try to break it up, we try to keep it simplified, but the bottom line is this: when you're looking at your digits, okay, just remember when you present your numbers that you cannot be more accurate than the least accurate number that you have to do whatever mathematical function you do. Now, what we broke it up to is the adding and subtracting part to make it hopefully more straightforward. And the thing to remember is when you add and subtract, you think decimal places. Because if you look at a number like 480 versus 480.1, obviously the 0.1 is a little more accurate because you went to the 10th place, okay? Whereas the number 480, you use some kind of equipment was used that didn't give you the accuracy than the number that give you up to the 10th place. So if I do a mathematical function like add or subtract those two numbers, then I got to remember the 480 has 0 decimal places. Therefore, even though my answer will have decimal places, okay, I need to round it up such that my answer has 0 decimal places. Again, you're governed by presenting your number with the accuracy of the least accurate number. The same is true if I multiply and divide. There we said, keep track of your sig figs. Because again, you're looking at sig figs with respect to the numbers, and you're looking for the least accuracy. So if I take that same number, 480, and I multiply and divide it by 480.1, my answer should have no more accuracy than the least number 480, the least accurate. So my answer will only have 2 sig figs at the final result. So think about how accurate you're going to present your data based on what you're doing mathematically to your numbers. And I realize that your calculator can split out X number of digits, and you may have the idea, well, if I put them all in there, then I'm being accurate. But no, that's not the case. It's the opposite. It's kind of counterintuitive of what you're thinking. You can't be more accurate than the least accurate number that you use to do whatever calculation you do, okay? So if you're still having trouble with that, feel free to email me and maybe give you some more examples, or come to the Zoom office time and we can go over some more examples, okay? Because sig figs is not going away. We use it throughout the semester. All right. I sent an email about the exam. It'll be open up this Saturday. You got 24 hours to look at it. I'm kind of governed by the department, so take a look at it. If you feel your answer is correct, by all means, shoot me an email. I'll go in there and look at it. And obviously, if it is correct, because maybe you added a space or something and you got counted wrong, I will correct it for you and give you your points, okay? So if those hours don't work, let me know. I might be able to have a little bit of latitude to give you some alternative times. I don't have much, but I can work, at least try to work something with you. Okay, so let's begin with, let's continue with chapter 5. Now, up to this point, in the previous chapter, we talked about how we came about the model. And we had J.J. Thomson, we had Chadwick, we had Rutherford. Based on their work, we determined that the atom consisted of a big a nucleus. And in the nucleus was the neutrons and the protons. And then the electrons were orbiting in some manner around the nucleus. Well, we didn't quite understand at this point, at least the science at the time, how were the electrons around it? How did they interact? How were they? I mean, were they just thrown in there like that plum pudding? Well, that's not the case. We further further data came along that demonstrated that these electrons exist in specific energy levels. And this is what this is all about. I also mentioned that the electron with respect to size is very tiny. And because of that, electrons have the property of acting like waves of light. And so what I got to do is kind of introduce you a little bit to light in the waves and frequency and wavelength. And then we're going to take that information and use it to demonstrate why it's been found that electrons exist in specific energy levels, okay? So let's talk about a wave. This diagram here would represent some type of wave, light wave. Now, I use the term electromagnetic radiation. A lot of times people hear that term and they only think about X-rays, but electromagnetic radiation, there's a lot of it. It goes all the way from radio waves to X-rays and gamma rays, okay? And they all travel like light. And to represent that, we have this diagram where you got these hills and troughs. Now, if we could mark a spot, let's say on top of the hill, and then go to the next hill, or the crest as is used here on your diagram, that is the distance that we can actually calculate. And that distance we call wavelength. So you may have heard the term wavelength someplace around, you're using sunblock, you talk about the certain wavelengths of light there, UV light there that is blocking. So that is the wavelength. That is the distance between, in this scenario, from one crest to another. Now you can pick any spot on one wave as long as you pick the same spot on the next wave, and that is the same distance, okay? Now, that symbol, which is called lambda, represents, is used to denote a wavelength. And that is the distance between the peaks here, between the crests. Now, frequency is a measure of how many wave cycles or how many wavelengths pass through a given time period. The majority of the time, we're talking about 1 second, okay? Now, I know you're familiar with frequency because some of you have computers that operate at, say, 2 gigahertz, or even your cell phone is operating at 1 gigahertz or something. That is a frequency. That's how many things happen within a given second, a time of 1 second. So 2 gigahertz, quite a bit of stuff going on pretty fast. Okay, so that's what frequency is all about. Now, if we look at these two descriptions of waves, two separate waves, we can see that the top one, the distance between crest and crest, is much longer than the bottom one, where the distance between two crests and the bottom here, you can see lengthwise is much smaller. So the top one represents a electromagnetic radiation with a long wavelength. The bottom one represents a short wavelength. Now, as the wavelength goes down with respect to amount or value, the frequency within a given second goes up, and the energy involved, all electromagnetic radiation has energy associated with it. And as the frequency goes up, the energy goes up, okay? We're all familiar with X-rays. X-rays are very, very powerful. They had a lot of energy in them. They're so strong, they can shoot right through you. They're very small. Hence, we can have X-rays of our bones. On the other end of the spectrum, we have radio waves. Same old radio waves you listen to your radio station, FM and AM. Those wavelengths are pretty large, not so much energy involved with them, okay? Now, if you're ever given a diagram and you're asked, I got two waves, A and B, the question may be asked, well, which wave has a higher energy, okay? And then which one has a lower frequency? We're looking at these two separate wavelengths. We see the top one has a pretty longer wavelength than the bottom one. So B would have a higher energy, shorter wavelength, higher energy. And the one with the lower frequency would be A, okay? And excuse me, at one given time, say 1 second, we can probably get like 2 or 3 wavelengths passing from B compared to A, where maybe 1 wavelength is emitted.
So I have a question.
Yeah, sure, Nathan, go ahead.
So you're saying that the shorter that the wavelengths are, from each other, the more energy that is being used.
That it has, that
Okay.
wavelength has.
Okay.
So I'll show you in the next slide how that comes, how you can visualize it.
Okay.
Okay.
Thank you.
All right. Okay, sure. Now we have what we call the electromagnetic spectrum. On the far right, we have radio waves. And these radio waves are very large. They're up in the meters range. On the far left, very short wavelengths. Okay. Those are the gamma rays, very deadly waves, by the way. Now, our eyes, this diagram is kind of skewed because what we see in the electromagnetic radiation is a very small amount, and it's denoted there in the middle with visible. Those are the colors the wavelengths that we can see. Our eyes have special cells called cones that pick up can pick up these particular wavelengths. We can't see ultraviolet. We cannot see infrared because we don't have the sensors for that, but we do have equipment that will measure those and they actually see it. Microwave, very close to the radio waves. That's how you make your popcorn, okay? And then, like I said, X-rays, taking X-rays of your body so you can look at broken bones and so forth. Pretty powerful. They go right through you. Now, previous chapter, we were talking about the 1900s. We had Rutherford and good old J.J. Thomson and so forth. They're all working in the 1900s. All this stuff is coming up. Well, 1900, another scientist, very famous, Max Planck. There's an institute in Europe called the Planck Institute, named after him. Anyway, what he proposed a very controversial idea at the time. And he said that energy was emitted in small bundles called quanta, okay? Small bundles called quanta. Now, he also suggested that energy was not continuous. It was thought that energy was just being subjected all over the place in one continuous mode. We find out that that's not the case either. He went on to define that an individual light of energy was called a photon. And Star Trek came up with photon torpedoes, okay? Anyway, little side note. So quantize basically tells you that energy exists in specific energy levels or amounts or quantities. It's not continuous. Best described by this diagram here, where the wedge on the left, where the ball's rolling, would depict continuous energy. It turns out that it's not the case. The energy can be best described by stair step. The bottom of the stair step is what we call the ground state. That is a stable state, okay? And to go up to another level, we have to add a specific amount of energy to go up to the first step and the third step and the fourth step, etc. Now, I want you to keep that in mind because if I share with you the periodic table that like I stated, I'll be using that quite a bit. If we look at the periodic table at the horizontal, let me make sure that I got this. Oh, wrong one. Okay. 1, 2, 3, 4, etc., all the way down to, I'll stop it here, but you can fill in the rest, 7. Okay, those are 7 energy levels. We call those periods. Okay, the periodic table has 7 of them. Those represent energy levels in which the electrons of these elements exist. But more on that here in a bit. So here comes, again, 1913, Niels Bohr, given all this information about light and knowing how electrons behave very similar to light, proposed that electrons around the nucleus occupy orbitals with distinct energy levels. He proposed the idea that electrons are quantized, okay? That was back in 1913. Now, these electrons exhibit or put themselves around the nucleus in a three-dimensional way. Okay, I know we have a lot of diagrams of two-dimensional, but nature's three-dimensional. So we got to think about three-dimensional when we talk about electrons here. Now, all these orbits are called energy levels or shells. Okay, the periodic table, as I demonstrated, has 7 energy levels, otherwise named periods. Okay, now every orbit has a specific radius. Every energy level has a specific radius and energy because there's a certain distance from the nucleus. Okay, so it's best demonstrated by this particular diagram here, where you have the nucleus in the center, and the dotted lines, again, think three-dimensionally, but here's two-dimensional picture, are the different energy levels. Level 1, level 2, level 3, which you can extrapolate and say period 1, period 2, period 3, all the way to period 7, okay? Now, how do we know this? Well, we've shown this by what are called line spectra, okay? Because it's been found that if we take an element or a gas and we put it in the sealed tube and then we hit it with electricity, we are able to, first of all, get light from it, hence fluorescent lights. We're all familiar with that. But furthermore, if we take that light that's emitted and subject it to analysis, we come up with something very interesting. We call that the emission line spectrum. Now, how does that work? Well, you get basically a fluorescent bulb. In this case, it's a bulb with hydrogen, okay? We hit it with electricity. What the electricity does, it excites the molecules, specifically the electron in hydrogen, and it excites it to another energy level. But nature being nature, it's difficult to keep that to stay in the excited state. It eventually drops back down to the stable level or ground state. And when it does, because the conservation of energy, the law of conservation of energy tells us that whatever energy you put into the system, you're going to get back the same amount of energy. And when it does that, it releases that energy as light. So we excite it, run it through these slits. All these slits do is just focus the light, and they run it through a prism. Much like the water droplets out here after it rains and you see a rainbow. The water droplets are breaking up the white light into the specific colors, which each have a specific wavelength. So when that occurs, you run through the prism, we find this spectrum, very distinct for hydrogen. This is the fingerprint for hydrogen, where we have a violet, blue-violet, and a blue-green light, and a red light. All of them can be calculated and assigned to them a specific wavelength, okay? A specific wavelength. Now, if you do this to a variety of different elements, in this example, you got lithium down to sodium, potassium, rubidium, cesium, and mercury, and neon, all of them have their own little fingerprint. So we can use this, for example, to identify what element we're looking at. It's a very good fingerprint to find elements for wherever we need to look for them. So it's very unique colors, very specific for the element. Each line represents a wavelength. Each line represents an energy level. So what's happening, like I explained earlier, is, for example, on the far left, this could be hydrogen. Obviously, it is because there's one electron denoted by the red color in the first energy level. It accepts the energy, it gets excited by energy, electricity. It kicks that electron up to the next energy level, okay? Well, it stays there for a period of time. Not going to hang out there very long. It's going to drop back to its ground state. And when it does, it releases energy. Now, a lot of times it releases energy as heat and light. So that little arrow there with a squiggly mark represents light that is being emitted. We see this all the time. You know, fluorescent bulbs for one, incandescent bulbs, even LEDs, even the screen that we're looking at right now. These are the molecules on the screen that are being excited by something on the computers that's creating your image, and we are visualizing the excitation of those molecules on that spot. But it happens so fast, it looks like it's continuous. If you have an electric stove, you turn it on, electricity runs through the coils, it excites the molecules, it's going to come back to the ground state. In that case, it gives off this energy as heat, and you're able to cook something. Okay? So it's either going to give off energy that again is light and or heat. So there are 7 energy levels that we have. Okay? Now, further analysis determines that within the energy levels, we have sublevels, also called orbits. Okay? There are 4 types of orbits. They are designated by these lowercase letters. They are the S orbit, the P orbit, the D as in David orbit, and the F orbit. Okay? Now, every energy level can be subdivided into these sublevels or orbits. Now, the very first energy level, which is first period, only has 1 orbit. We denote that by the letter S, and that coefficient 1 tells you that that is the first energy level. S represents that first orbit, okay? There's only 1 sublevel or orbit in the first energy level, which encompasses hydrogen and helium from the periodic table. As we move to the second energy level, which starts with lithium on the far side of the periodic table and shoots across the periodic table to neon, it contains 2 orbits. It also contains the S, but we introduce a new orbit, which are called the P, okay? Bear in mind, the first energy level does not have any P orbits, only the second. Now, all orbits from 1 through 7 have in common the S. So every one of them contains the S. So the third energy level, which begins with sodium on the periodic table, number 11, and shoots across to argon, okay, on the periodic table, are represented by the third energy level. There is an introduction of a new orbit called the D. So it also has the S, it also has the P, but now we introduce what are called the D orbit, okay? And then finally, not finally, but the fourth energy level, which is the fourth period beginning with potassium and shooting all the way across to argon, we introduce the other orbit called the F. So it also contains, the fourth level contains the S and the P and the D, and now we bring in the F, okay? Now, so this diagram kind of, yes.
Quick question. What about
Sure.
level 5, 6, and 7 for G?
It will continue. They haven't got the G's yet, but if we move up with more elements, right now when we get to 5, we won't find any F's in there, okay?
Gotcha. All right.
Yeah, we won't find any F's because we're already, the fourth level, we're talking about the sixth period.
Sorry, I worked ahead a little bit. My bad.
Okay, no problem. Yeah, but if we find more elements, you know, beyond 118, and we continue, then we're going to start getting to the G's and so forth.
Okay.
Okay. All right. Good question. All right. So this diagram kind of breaks it down for you. We got level 1 through 4, or period 1 through 4. The first energy level only has the S orbits. The second has the S and the P. The third has S, P, and D, and so forth. S, P, D, and F for the fourth. Okay. All right. Now, what these orbits represent are very interesting, but they're basically mathematical equations, humongous mathematical equations. And if you take that equation and you plot it, what that shows, you plot data to that equation, you have an image that represents the probability of finding an electron in that given space. Okay. Now, thing to remember here that every orbital can hold a maximum of 2 electrons. Okay, 2 electrons per orbital. Okay, now there's only one s orbital, so it can hold a maximum of 2 electrons. Now, with respect to the p, there are 3 p orbitals. 3, each one can handle 2 electrons, so there's a maximum of 6 electrons for the p. The d has 5 orbits, and each one can handle 2 electrons. So at the most, for the d orbits, we can put in 10 electrons. And for the f, there are 7 orbitals of the f. And each one with 2, we can put in a maximum of 14 electrons into the f orbitals, okay? Now, let me shoot back to the periodic table for a second. Because I always refer to the periodic table because it does give you a ton of information. Here's an introduction. We got the period that I just wrote here that show you, okay, those are the energy levels. I'm going to take it one step more. We have a slide like this, but I want to talk about it. I'll show you a slide, but I want to give you a little bit more discussion in it. If I take the periodic table and I highlight, remember, we have the Roman numerals on top. We got Roman numeral 1 and 2A, just the A's, okay? If I encompass the 1A and the 2A, okay, I want you to think about those elements in there as the S elements, okay? Those are the S elements. Notice there's 2 columns in the S elements. How many electrons can we put in the S orbital? 2, okay? Now let's shoot over here, starting with 3A and shooting across all the way to 8A. I'm going to highlight it here, okay? Think of those as the P elements. And we just stated that there's 3 P orbitals. Each one can handle 2. We can have 6 electrons in the P elements. Count the number of columns in the blue. There should be 6 columns there, okay? Let me do a different color. Now, taking these elements here, they have their special name. They're called intertransition elements. But think of these guys as the D elements, D as in David, okay? D, there was 5 D orbits. Each one can handle 2, total of 10 electrons. You should count 10 columns there in the yellow area. And then finally, let me pick a different color. These down here in the bottom, which have their own little name, the lanthanide and the actinide series. Think of these as the F, okay? And guess what? F has 7 F orbitals, 2 electrons per F, that's 14. There should be 14 columns there, okay? So the periodic table can really help you to do what we're going to be talking about right now is doing what we call the electron configuration. What the electron configuration is nothing more than how to display where the electrons are. And from the electron configurations, we're going to be able to determine a multiple of other things. Let's go back to this. Okay. So this diagram here shows you the levels and the orbits. Now, there's a little box. In every little box, you can handle, it represents an orbit, you can handle 2 electrons. So if I were starting with hydrogen, hydrogen has 1 electron, right? So that arrow represents one electron. 1s1. 1 means superscript 1. If I go across the periodic table, I go to helium, and how many electrons does helium have? Well, it's got 2 electrons. So that arrow going the opposite direction represents the second electron. There's a rule that says they can't go in the same direction. They go a separate direction. One goes one way, one goes the other one. Okay, so we're at helium. Now, taking the periodic table and keep going around the horn, so to speak, we go to lithium. Lithium is element number 3. Lithium has 3 electrons. Well, guess what? I put it right there in the 2s1. 3 electrons, 3 arrows. And I keep going across the periodic table next door to beryllium, has 4 electrons. Okay, so that's 2s superscript 2. From beryllium, we shoot across to boron, okay, number 5. It has 1 electron and 1 more electron, 5. We got 5 electrons here. Continue across to carbon. We go to the next box. We got to fill up each box first. That's total of 6 electrons. From carbon, next door to carbon is nitrogen. Now we'll fill that up. Nitrogen has 7, right? 7 electrons. From nitrogen, next door is oxygen. Now we fill up the other box. Oxygen has 8 electrons. And then from oxygen, after oxygen is fluorine. It has 9 electrons, excuse me. Okay. Now, the last one, which is neon, which is number 10, it has 10 electrons. Okay. And so we're already up to neon as far as electrons are concerned. Okay. Now, if we go around the horn, because after neon is sodium, sodium's in the 3rd period, and it has 11 electrons. That's where that electron will go. It has to go to the next level and continue on as we proceed. Okay, all the way across the periodic table.
Dr. Fred?
Yes, go ahead.
Question. Sorry, I'm only asking because I wasn't for sure. So do the
Yeah.
arrows make a difference? Which way they're
Well, yeah.
facing? Does that even matter? I mean,
Yeah, when you're filling in the box, always have one arrow go one direction, the other arrow going in the opposite direction. There's a rule we're not going to talk about, but it's beyond the scope here. But when 2 electrons are in one orbit, one has to go in one direction, the other one has to go in the other direction.
I think she was asking, does it matter in the order in which they're facing? So does it matter, does one have to go up first, or can it go down and then up? Does it matter?
Doesn't matter. You start up with one arrow up, the next one goes one arrow down, or vice versa. Just as long as they're in opposite direction.
okay. That's what I was asking. Thank you.
Yeah, it doesn't make a difference which direction. In fact, we couldn't even really define which way it's going, to tell you the truth. But we do know that when there's 2 in one orbit, they're in opposite direction.
Okay. And are those going to be on any of our upcoming activities as well? Like something like this?
Probably not, but something like what's coming up may likely be there.
Okay. Thank you.
Okay? This is more to demonstrate how the energy level, the orbits are filled up as we move up to a bigger electron with a bigger element with more electrons. Okay? Because we can fill up all of these up with all the electrons, all the 118. Okay? All right, so let's move on. So the s orbitals are basically a sphere, they're round. Excuse me. And that diagram on the right is a plot of that equation I mentioned to you in all 3 directions, of which represents what is called the s orbit. And if you take data, apply it, you end up with an equation like this, where that area represents a probability of an electron being in that spot at any given time period. These things are moving around so much, you really can't really pinpoint it in one moment in time, because the moment you pick it, it's gone someplace else. Okay, now, with respect to the P, remember we said there are 3 P orbits, okay? And again, they are 3 different mathematical equations that when you plot the data in the 3 axes, X, Y, and Z, you come up with this particular shape that we call the dumbbell shape. Okay, so this one on the far left is along the x-axis, the one in the middle is along the z-axis, and along the y-axis is the one on the far right. All these, if you can imagine, if you can bring them together, they're all together. They're not separate. They're all put together dimensionally. Now we won't show you the D's. What this link does, it takes you to a site that's not functioning right, but we're not too concerned. I can tell you this, the D's and the S, there are some crazy looking orbits. Crazy looking orbits. They kind of look like space stations and some of these things. So we're not going to talk too much about those, other than this, the S are round and the P's are dumbbell shaped, and there's 3 of them, okay? And as far as the D, there's 5 of them, and the F, there's 7 of them. Okay, now we're going to get into what's called the electron configuration. And that is a method of how to depict where the electrons exist in the elements. Now, the book gives you this particular diagram, and there's the order that you have down at the bottom in blue, where you start off with the 1s. The 1 number, okay, the coefficient, is the energy level. The S, obviously, is the orbit, okay? Now, we're going to start adding superscripts on the letter. Remember that the maximum number for the S is 2, the maximum number for the P is 6, and for the D is 10, and the F is 14, okay? So you're going to see a superscript here in a bit. So you can use this diagram, okay? Or you can use the periodic table to help you out. Now, let me go back to the periodic table. All right, so if I start off with, hopefully we can see this here. Let's start off with hydrogen. Hydrogen's number 1. It's got 1 electron. So its electron will be in the first energy level, correct? And in the first energy level, all we have is the s orbit. So we put down s. And then hydrogen only has 1 electron. Now I can't do superscript here, but that represents my superscript. And I put a 1, okay? So that denotes the electron configuration of hydrogen. Okay. Now, as I shoot across the table, we go to helium. Helium has 2 electrons, correct? To demonstrate its electron configuration, I simply change that 1 to 2. And that is the electron configuration of helium. Okay. Now, I come around to lithium. Okay, lithium has 3 electrons. Well, the first 2 are full in the 1s2 orbit, energy level. But then, look at lithium, it's in the second period. So that begins the 2s orbit. And it has 1 electron in that orbit. Okay, so 2 of them are in the 1s, and 1 of them is in the 2s. Now, if we go to beryllium, the neighbor next door, number 4, well, we simply change that 1 to 2, okay? Notice those columns 1 and 2. I said earlier, think of those as the s electrons. So the s orbitals get full there first. Now, if we shoot across to number 5, remember I highlighted those 6 columns? I said, think of those as the P. That is where the P orbits begin. Now, we're still in the second energy level, okay? But the P's begin. So that for boron is 2p1. Now count all the superscripts, okay? I should have 5 superscripts representing 5 electrons. For boron, of those 5 electrons, 3 of them are in the second energy level, and the other 2 are in the next energy level in. And guess what? When I go to carbon, I'm just shooting across. I add 1 more, okay? That's the 2p2 for carbon. Nitrogen, guess what that would be? 2p3, okay? For nitrogen, and I continue, now stop there for nitrogen. Nitrogen's in group 5, see the Roman numeral 5, okay? On the energy level 2, we got 5 electrons. Okay, which brings me to the point. The outermost shell of the energy, the outermost energy shell that has electrons are called valence electrons. The innermost are called the core. Now the innermost are full, okay? The outermost, that's where all the action happens. That's where all the chemistry occurs, on the outermost shell. Okay? And so if you look at nitrogen, which is in group 5, it contains 5 valence electrons, which are denoted there by the 2s2 and the 2p3. Okay? Move across to oxygen, just change that 3 to 4, and now we have 8 total electrons. Of those 8, 6 of them are in the outermost shell. Continue to go to fluorine. We just switch that up to 5. Fluorine has 9 electrons. Okay. Of those 9, 7 of them are in the outermost shell. And then finally, when we get to neon, we change that 5 to 6. And that is the electron configuration for neon, okay? So neon has, it's in group 8. Neon has 8 valence electrons on the outermost shell, which in this case is the second period, okay? It has that magic 8. The driving force for any chemical reaction that we're going to be talking about is to get 8 valence shells in their orbits, either by gaining an electron or losing an electron. Okay, so now let's go to sodium, number 11. We went around the horn here, okay? Sodium is in the 3rd energy level. It's one of the s electrons. So it's the 3rd energy level, it's the s electron, and there's only 1, because it's in group 1, 1a, 1 valence electron. So sodium has 11 valence electrons, okay? But only 1 of them is in the outermost shell, okay? Now, I want to ask you guys a question. You tell me, give me your best thought. I just stated that the driving force is to gain 8 electrons. And so sodium right here has 1 electron in the outermost shell. It needs to, elements want to have 8 electrons in the outermost shell, either by gaining or losing. Would you predict that sodium, would you think sodium would be easier to gain 7 electrons or to lose 1 from an energy perspective? What would you think?
It'd be easier to lose 1.
Exactly. Remember, Mother Nature's not gonna, is gonna take the easy route. So sodium is wanting to lose that 1 electron sitting in the outermost shell. Much easier than gaining 2 electrons. Okay, let me back it up for a second. Let's go back to fluorine. Remember fluorine? Fluorine's number 9. Okay? Now give it some thought. In the valence shell, fluorine has 7 electrons. again, I pose a question. Do you think from an energy perspective, gain 1 electron or lose 7?
Gain 1.
Very good. Yeah, that's what these guys want to do. Anything to fill up that 1 electron. Okay, somebody has their mute, their speaker on. Okay, there we go. It's gone. I was getting the reverb here. Okay, so they want to gain electrons, which now you could start bringing a conclusion here. Those guys, fluorine, chlorine, bromine, oxygen, nitrogen, they're very close to the noble gas. They are all nonmetals. Nonmetals, put this in long-term memory, nonmetals want to gain electrons. Metals, all the metals want to lose electrons. The nonmetals, by gaining an electron, now have an electron configuration like the noble gas in front of it. The noble gases are inert. They're happy. They got their 8. They're not going to react because it takes too much energy to yank an electron off when you got that happy 8. Okay? And so that's why nonmetals want to gain electrons. Now, if I gain an electron, what do you think happens to the overall charge of let's say, fluorine? Fluorine element is neutral. It has 9 protons, 9 electrons. Okay? 9 protons, 9 electrons. What's my net charge for the element? 0, right? Now, by picking up 1 electron, because it needs 1 electron to have that 8, now it has 9 protons and 10 electrons. What is my net charge?
+1.
I think, try again. I got 9 positives.
-1.
You got it. And so that is the ion. Yeah, now you created, by gaining 1 electron, you made a negative ion. Sodium, on the other hand, remember we talked about that? Sodium, which had this configuration, 3s1, has 11 protons and 11 electrons. When it loses that 1 electron, now it has 11 protons and 10 electrons. What's my net charge now?
Wait, can you say that one more time?
I got sodium has 11 protons, and when it loses 1 electron, now it has 10 electrons. What is my net charge?
Oh, +1.
Exactly. So sodium, by losing that 1 electron, because it's a lot more energetically favored, now has a positive charge. And that is what we are ingesting. Is now called an ion. It's an element with 11 and 11 electrons, but it loses 1 electron, now it becomes an ion. And that is what you're putting on your French fries, not the sodium element, but the sodium element. The same with fluoride. Fluoride is used in toothpaste, stannous fluoride. You're not brushing your teeth with fluorine, you're brushing your teeth with fluoride. Fluoride is fluorine that gain 1 electron to become the ion, okay? So that example here about electron configuration is just a matter of filling up the electrons. Now, the trouble place that happens is this. When we get to element number 21, okay, element number, scandium is, let me mark it. Right here. Okay. Now, number 21 is in the 4th energy level. Also is part of the D elements. So you would think, okay, when I get to that element, I should be calling that 4D1 for that electron. And that's a reasonable conclusion. However, what has happened from the mathematics of this, that the D orbits for those elements, starting with period 4, 5, 6, and 7, they are actually 1 energy level in. So even though number 21 is in the 4th energy level, its D orbit is really in the 3rd energy level. And that's why you get 3D. It is coming from the elements in the 4th period. The elements starting with 39, that's in the 5th period. Those d orbits start coming in, the 4th, 1, 2, 3, 4, in the 5th period, they start coming in the 4D energy level, okay? But we're asking you guys to be able to do the electron configuration of at least up to 20. And basically, I already got you up to sodium, and the rest is simply following what I just did, using the periodic table, okay, and knowing its position on the periodic table. Alternatively, you can memorize that little sequence there. Okay, you notice here's that 3D. You don't have to worry about that 3D until you hit number 21. Okay, so it's before 21, 3D doesn't even come into play. All right. So you have a couple of ways. I prefer the periodic table because not only is it telling me a whole bunch of information as far as energy level, it's telling me how many valence electrons it has, what is the charge it would be if I lose an electron, and so forth. I'll have more on that later on. So here's the electron configuration of carbon. And we went through carbon in that example I just did. So remember, the coefficient is the energy level. So we got 1s2. The superscript is the number of electrons in that orbit. All right, carbon has a total of 6 electrons, okay? Of those 6 electrons, 4 of them are what are called the valence electrons, are in the outermost shell, right there, okay? And you're in the 2nd energy level. 2 of them, of the 4, 2 of them are in the S and 2 of them are in the P. In fact, that's where all the reaction occurs, right on the valence shell, the outermost shell. Okay, this is a rehash of what I went through earlier, again with the boxes. This diagram actually should be flipped upside down, really, because you start off at the bottom at level 1, and it should be more like an upside down pyramid to be more accurate, if you will. Okay, but same stuff. You start off with the S first, you fill that up, the 1S. And when you're in the 2nd level, you fill up the 2S, then you fill up the P. And then 3 level, the same scenario. That is the order of filling up the orbits. The S first, then the P, then the D, and then the F if you need to fill it up, or the last ones to fill up. Okay. This is a demonstration of the electron configuration of sodium, oxygen, calcium, and chlorine, okay? That shows you where the electrons are. Sodium we just did. Sodium has its valence shell. That 1 electron all by itself is in the 3rd energy level, okay? Oxygen has 6 valence electrons in the 2nd energy level. 4 of them are in the P, 2 of them are in the S. Calcium, guess what? Calcium it's in the 4th energy level, and it's part of the S elements, and it's in the 2nd column over, so it's 4s2, okay? Let me ask you a question. Calcium, do you think it would lose electrons or gain electrons?
Gain an electron.
Mm.
Wait. No, it's lose. It's lose an electron.
Right.
I was debating. I was like trying to look at the periodic table, and I was debating on it.
Okay. Well, first thing, when you're asked that question, first thing you should look at, is it a metal? If it's a metal, lose electrons, no questions asked. Not sure? Look at the electron configuration. It's 4s2. In order to make that 4 energy level happy, it needs to gain a whole bunch of electrons. So would it be easier from an energy perspective to gain all those electrons or lose 2? Like sodium, much easier from an energy perspective to lose 2 electrons. So if calcium lost 2 electrons, what will be its new charge? Any idea? If the calcium element were to lose those 2 electrons in the 4s, what will be the charge of the new species created called the calcium ion?
Wouldn't it be +2 because it's losing 2 electrons?
You got it, exactly. If you have a trouble remembering what happens to your charge, think of it in human terms. If you lose negativity, don't you become more of a positive person? Okay, one way to look at it. And the converse of that, if you gain negativity, don't you become more of a negative person? All right, so maybe that would help you. Okay, we're going to have special names for that later down the road, losing and gaining electrons. And then we did fluorine, but chlorine's the same scenario. The valence electrons are denoted here in the 3rd energy level. 2 of them are in the S, 5 of them are in the P. Now, here's the thing about the periodic table. Back to the periodic table. The reason they're in the columns and in the same group is because they share something. Everyone there in the same group shares something. For example, let me make sure I change my color here. Everybody here are in group 1. Every one of those elements share 1 valence electron. Every one of them. Hydrogen has 1 electron. Lithium has, we went through the electron configuration, it has 1 valence electron in the 2s1 level. Sodium is the same way. Its valence electron is in the 3s1 level. Potassium is the same way. And because they share that 1 valence electron, guess what? With respect to reactivity, they share that too. Simply because they each have the same valence electrons and therefore will react very similar. Take a look at way on the other side of the spectrum, under group 7. All of them have 7 valence electrons. We did fluorine and we just had chlorine there. Bromine's the same way, iodine, okay? Let me clarify this. They all have different total number of electrons, but the outermost layer of those electrons are the same number, 7. Fluorine has 9 total electrons. 7 of them are on the outside. Chlorine has 17 total electrons. Again, 7 on the outside. All the way down to number 85. It has 85 electrons, but still has 7 around. Okay? So that's why they're put in the same column, because they share that property. The same is true for everybody in group 5. They all share 5 valence electrons. Hence, they all have similar reactivities. Now, the noble gases, again, they all share 8. And they're called noble gases because they obtain what's called the magic 8. The drive is to have 8 valence electrons in their outermost shell. And noble gases have achieved that. Therefore, they're very unreactive, hence the term noble gases. The exception to the rule is helium. Helium does not have 8, it has 2. Its rule is a duet, but 1s2, its outermost shell is full. Okay? So, excuse me. Now, and we can only say this trend for the A, the 1A all the way to 8A. The B, these guys in here, not so much. They vary as far as how many electrons they lose and the gain. But much more on that much later on. So let's go back to the element. All right, so that's the electron configuration of different elements. Practice on writing the electron configuration. Okay. Now, earlier I stated when I highlighted the periodic table, think of these elements as the S and think of them as the P. Well, this periodic table are color coded to tell you the same thing. Group 1 and 2, think of those as the S. You got S1 in the first column, S2 in the second column, etc. We got in the yellow are the P's, there should be 6 columns. And the D's, there should be 10 columns, and the F's, there should be 14 columns. Now, if you ever need to get into number 21 or other, we just fill it up across the table. So number SC, scandium, which I denote right here, that would be D1. And if we go all the way across to zinc, that would be D10 for its electrons. Okay?
Just a quick question.
Sure.
So the color coding is that like there will be like an S in the first 2 columns, there will be a D in the middle columns, and then there will be a P and F in those in their color coded columns.
That is correct. So
Okay.
if you got, let's say, let me highlight one. If you were doing aluminum right here, okay? Well, all the previous energy levels before it are full. And if you go across the periodic table, the S are full, so that would be the 3s2, and then we will start with the P with aluminum. Okay, so it would be P1 for aluminum, and if we went across the table for argon, that would be P6. Okay, now the ones that are reddish color, like number 21 here, those are the D. That's where the D orbits begin, but you will not see them until you hit that element. Okay, the same would be true for these other elements down here. They're not there until you actually going to start working in those elements. Now, the likelihood of you guys doing the F is pretty low, possibly maybe a couple of D's, at least in the 4th period. So, but be familiar with the S and the P for sure. Okay. Now, what this does is using the periodic table. Now, the ones in the middle, the D elements, and you notice the number, this is what they are in real life, so to speak. But for Chem 130, we're just going to go sequentially for the D, D1, D2, D3, and then all the way to D10. The same is true for F, because they do hop around depending on the element, okay? But you can see where that's the electron configuration for all the elements that we have. Notice number 21, even though it is in the 4th period, that is where the D kicks in, but that's this one right here. But it is, even though it's in the 4th period for number 21, the D orbitals actually begin in the 3rd energy level. Hence, that's why there's a 3D in front of that, all the way across. The next one, it's in the 5th period, but the energy level for the D starts off in the 4th energy level. And to confuse it a little bit more, beginning here, for that one I just highlighted, that's where the F orbits, they don't begin in their particular period, which is 6th period. They actually begin 2 periods in. So hence you see, even though this one I highlighted, I circled, is in the 6th energy level, the F orbit actually begins in the 4th energy level. And that has to do with the mathematics involved with respect to the orbits. These mathematics are pretty intense. There's an area called quantum mechanics. Pretty hefty mathematics. Anyway, noble gases, very stable, and as the book calls it, happy. I don't know if they're happy, but I do know that they have an octet. And if that makes them happy, okay. I would have used the word unreactive. Probably would have been better. Okay. Why? Because the octet is full. All the levels are full, except helium. Helium, it's only its S level is full. It doesn't have 8. Okay, so that configuration, S2P6, is a very stable configuration, be it whatever energy level starting from 2 forward. Okay, so that is the driving force for chemical reactions, is for the elements, depending on whom they are. Either if it's a metal, it's going to lose those electrons. So now its electron configuration is very similar to the noble gas behind it. Or if it's a non-metal, like chlorine, fluorine, it's going to gain an electron. So its electron configuration is similar to the noble gas in front of it. Now, that's the key word. I didn't say fluorine, back to the periodic table. I didn't say fluorine by gaining an electron became neon, okay? Fluorine's right here. Fluorine has 1s2, 2s2, 2p5. That's the electron configuration. We just talked about it, wanting to gain 1 electron. By gaining 1 electron, now it has 10 electrons like neon, okay? It did not become neon. How could fluorine, what would need to happen for fluorine to become neon? Can anybody tell me?
That you add a proton.
Exactly. Remember we said proton defines what the element is. You can lose neutrons and electrons or gain them all day long. You don't change that element. And so fluorine, by gaining 1 electron, now has the same number of electrons as neon, and the octets fulfilled. That is called isoelectronic. It has the same electrons as the noble gas in front of it. Sodium, way over here, has that 1 valence electron. By losing it, it also now has 10 electrons. It becomes isoelectronic like neon. So fluorine becomes fluoride, and now it's isoelectronic with neon. And sodium becomes sodium ion, and it's isoelectronic with neon. Okay? No, not too advanced, Nick. The mathematics will make them very, very advanced. Yeah, but there is a trend, and the way to go through this is to, as far as electron configuration, is to do some electron configurations, and be familiar with at least the first 20, okay? Because we're going to see here in a moment how, by losing and gaining, what's happening with respect to the chemicals and reactions to what's happening with the reactions and why things happen as they happen. All right, let's go back to this one. All right, I talked about the valence electrons. I talked about the core electrons, okay? All the actions in the valence electrons, that's where all the reactions occur. Now let's take up the electron configuration of phosphorus, okay? It's given here, 1s2, 2s2, 2p6, 3s2, 3p3. It has 5 valence electrons. Look at your periodic table. It's in group 5a. Oh, so that tells you group 5a, 5 valence electrons. Now, it is a non-metal. Being a non-metal, it's going to gain 3 electrons because the p orbit is empty. It has space for 3 electrons. And once it does that, it will be isoelectronic with argon, okay? There's a driving force. And phosphorus will be, once it gains 3 electrons, it has a total -3 charge, okay? And we have to change its name. Now when it becomes an ion, it becomes phosphide, okay? Fluorine, when it becomes an ion, becomes fluoride. Chlorine becomes chloride, okay? Iodine becomes iodide. It is the nonmetals, an introduction to the naming of these compounds, that when they become ions, by gaining electrons, we change their name from the INE to the IDE ending. Chloride, chloride. Oxygen becomes oxide. Phosphorus becomes phosphide. Okay. There's the valence electrons. If we look at chlorine, we talked about this. We ran a few examples there. That's the electron configuration of chlorine. Valence electrons, 3s2, 3p5. Okay. Has 7 valence electrons. Beryllium, okay, it is in group 2. It has 2 valence electrons, and it's a metal, so it's going to lose electrons. Aluminum has 3 valence electrons. It is in group 3a. Okay, those 3 electrons are 3s2, 3p1. But because aluminum is a metal, it's going to lose those 3 electrons and end up with a positive 3 charge. All right. Now, this is the group number because it will help you to remember how many valence electrons it has, but based on what group number it's in for the A elements. So group 1A, 2A, 3A, 4A, 5A, etc. They each have 1, 2, 3 valence electrons, okay? The only exception is, again, helium, which has 2. So here, you can use the periodic table and at a glance be able to determine, one, if we look at let's highlight one real quick. If we look at silicon, okay? Now, silicon is what do you know just by its position? One, it's a metalloid, it's on the star stack. 2, it has 14 protons, 14 electrons. Can anybody tell me how many neutrons it has?
14.
14. 14 protons, 14 electrons, and 14 neutrons, okay? You know its atomic weight because it's given there. Okay, you also know its electron configuration based on where it's at. It's in the 3rd energy level. So 1s2 is full, 2s2 is full, 2p6 is full, then 3s2 is full, and then 3p2. There's the electron configuration, okay? So now, how many valence electrons does it have? Well, it's in group 4, it has 4 valence electrons, okay? Now you might ask, would it lose 4 or gain 4? Because the driving force is 8. Well, here's a special thing about the guys in group 4. They're on the fence because it takes just as much energy to gain 4 as it does to lose 4. So depending on the interaction conditions, they can gain 4 electrons or lose 4, okay? So as a kind of a benchmark, group 4 kind of tells you, well, it depends on conditions. That means that from group 5 forward, they gain electrons. And from the metals 5 back, they lose electrons, okay? All right, so not only that, can you tell me who's bigger in diameter, carbon or silicon? Just based on its position on a periodic table.
Silicon.
Silicon.
Silicon, exactly. It's in the 3rd period, okay? It's much bigger. So do we have to memorize that? No, we just have to find it in a periodic table. Okay, if we look at, well, almost any element there now, krypton, little Superman's nemesis, okay? Krypton has 36 protons, 36 electrons. You can calculate the neutrons, okay? It has how many valence electrons?
7. No, 8.
8? Yeah, exactly. It's got 8 electrons. So of those 36, 8 of them are there, okay? Who's bigger in size, fluorine or krypton?
Krypton.
Exactly, krypton, because it's in the 4th energy level. It's just bigger. It's just a bigger ball, okay? And so just using your product table, we can know all that information. All right. Let's clear this out. And or you know what? I'm thinking we reached that time. Well, let me stop it here on slide 33. Okay. Any questions?